Welcome back to Decentralized Application Development Crashcasts. I'm Sheila, and as always, I'm joined by my co-host, Victor. Before we dive in, I'd like to remind our listeners that your feedback means the world to us. If you're enjoying the show, please take a moment to rate us on your favorite podcast platform. It really helps us reach more developers like you.
Absolutely, Sheila. Your support keeps us going. And speaking of going, shall we jump into today's topic?
Definitely. We're continuing our journey through Season 2, focusing on core hole-punch technologies. We're in Chapter 3, discussing the Hypercore protocol, and today we'll be exploring tree structures and Merkle trees. But before we start, I have a quiz question for our listeners. Ready?
Ooh, I love a good quiz. Let's hear it.
All right, here goes. In a Merkle tree with 1 million leaf nodes, approximately how many nodes would you need to verify to prove that a specific piece of data is included in the tree?
Now that's an intriguing question. It really gets to the heart of why Merkle trees are so powerful. Without giving away the answer, I think our listeners will be surprised by how efficient these structures can be. It's a great way to think about the scalability of verification in decentralized systems.
Exactly. We'll reveal the answer at the end of the episode. Now, Victor, could you start by explaining what tree structures are in the context of data management?
Sure thing, Sheila. In computer science, a tree structure is a way of organizing data hierarchically. Imagine a family tree. You have a root, like a common ancestor, branches representing different generations or family lines, and leaves, individual family members. In data structures, it works similarly. You have a root node at the top, and it branches out to child nodes, forming a hierarchy.
That's a great analogy. So how do tree structures relate to Merkle trees, and why are they important in Hypercore?
Excellent question. Merkle trees are a special kind of tree structure named after Ralph Merkle, who invented them in 1979. What makes them unique is that each non-leaf node is labeled with the hash of the labels or values of its child nodes. This creates a cryptographic seal for the entire data structure.
Fascinating. So, if I understand correctly, this means that any change in the data would result in a change in the hash all the way up to the root of the tree.
Exactly right, Sheila. This property makes Merkle trees incredibly useful for verifying the integrity of data, especially in distributed systems like Hypercore. Even a tiny change in any part of the data will cause a ripple effect, changing the root hash.
That's really powerful. But I'm curious, how does Hypercore specifically utilize Merkle trees?
Great question. In Hypercore, Merkle trees are used to create an append-only log that can be efficiently verified. Each piece of data added to the Hypercore becomes a leaf in the Merkle tree. The tree structure allows for quick verification of data integrity and efficient synchronization between peers.
I see. So, it's not just about storing data, but also about making it easy to check if the data has been tampered with.
Precisely. And there's more. Merkle trees in Hypercore also enable something called proof of inclusion. This means you can prove that a specific piece of data is part of the dataset without having to share the entire dataset.
That sounds incredibly useful for decentralized systems. Can you elaborate on how that works?
Certainly. Let's say you have a massive dataset, but you only want to prove that one specific data point is included. With a Merkle tree, you only need to provide the hashes of the nodes along the path from your data point to the root. This is much more efficient than transferring and verifying the entire dataset.
Wow, that's really efficient. It reminds me of how you might prove you're part of a family by showing just your direct lineage, rather than the entire family tree. Are there any common misconceptions or pitfalls when working with Merkle trees in decentralized systems?
Good analogy, Sheila. And yes, there are a few things to watch out for. One common misconception is thinking that Merkle trees provide confidentiality. They're great for integrity and proof of inclusion, but they don't encrypt the data. Another pitfall is not considering the trade-off between tree depth and verification time. Deeper trees can store more data, but require more steps for verification.
Those are important points to keep in mind. Before we wrap up, do you have any interesting facts about Merkle trees?
As a matter of fact, I do. Did you know that Merkle trees are a fundamental part of how Bitcoin and many other cryptocurrencies work? They use Merkle trees to efficiently summarize all the transactions in a block, allowing for quick verification of transactions without needing to download the entire blockchain.
That's fascinating. It really shows how versatile and powerful this concept is. Now, let's reveal the answer to our quiz question. Victor, would you like to do the honors?
I'd be delighted. The answer to our quiz question is, you would only need to verify about 20 nodes to prove that a specific piece of data is included in a Merkle tree with 1 million leaf nodes. This is because the number of nodes you need to check is logarithmic to the total number of leaves, which is what makes Merkle trees so efficient for large datasets.
That's incredible efficiency. To wrap up, let's summarize the key points we've covered today. 1. Tree structures in data management are hierarchical organizations of data. 2. Merkle trees are special trees where each non-leaf node is a hash of its children. 3. Hypercore uses Merkle trees for efficient data verification and synchronization. 4. Merkle trees enable proof of inclusion without sharing entire datasets. 5. While great for integrity, Merkle trees don't provide data confidentiality. Victor, any final thoughts?
Just that understanding Merkle trees is crucial for anyone working with decentralized systems. They're a powerful tool that enables efficient, secure, and scalable data management in peer-to-peer networks.
Absolutely. And with that, we'll wrap up today's episode. Remember, if you enjoyed this content, please visit crashcasts.com, join our Discord community, or support us on Patreon. Your engagement helps us create more great content for you. Until next time, happy coding.